Welcome to the Wastewater Treatment Certification webinar series. This is Chapter 8, Flow Measurements, and the presenter for this presentation is John Walker. When we want to measure flows in a water treatment system or a distribution or collection system, there are two ways that we can do it. One is in a system that is closed, what we will call closed channel flow systems. And this is where we have pipes that are usually completely filled. And the way we measure flows in this through different types of flow meters, such as a Venturi flow meter, ultrasonic methods, magnetic methods, or a pitot tube. We're not going to talk about these closed channel because much of what we will measure in terms of wastewater will be in what we call open channel flow systems, which is flow in any channel which has an open surface to the atmosphere. So if you think about rivers and canals, anything else that's uncovered, those are what we will call open channel, and the ways in which we measure the flow in those are slightly different than a closed channel or a pipe. So a little introduction to how we measure flow. The first one we will look at is what we call a timed gravimetric system. And that's where we are going to collect the flow in a body of water in a container of fixed volume for a certain amount of time. And if we know that we have a 5-gallon bucket and that it takes a minute to fill that bucket, we know the flow is 5 gallons per minute. Of course, you probably need a lot of buckets if you're going to do this. The other way we can test the flow or measure the flow is using a dilution. So if you add amount of dye, for example, fluorescent dye, or maybe even other certain types of markers, radioactive markers, then how much that is diluted over a period of time will give you an idea of the flow rate. At the bottom, there is a website that will go over methods of measuring flows in a little more detail. So if you want to write that down or search for that, that can be very helpful to you. Other ways of measuring flow that are in odd-shaped channels or in pipes uses the slope and the diameter of the pipe or the radius of the pipe. This uses something called the Manning equation, and this is best left up to the engineers. The other way of measuring flow, which we will see in other areas of this class, is to, once we know the area, the cross-sectional area of a pipe and the velocity of water flowing through that, then we can calculate the flow. But in a wastewater treatment, you probably are going to use one of the following two structures, weirs or flumes. We call these hydraulic structures because water flows through them. And in order to get accurate flows through a weir or a flume, you're going to need two separate measurements. The average velocity flowing through that structure and the depth of water that's flowing either over a weir or through a flume. So what do we mean by a hydraulic structure? Well, this is really a device that's introduced into the flow of water so that we have a known relationship between the level of liquid or water in that structure and the flow rate of the stream. So one of the reasons we use weirs and flumes is that all the flow is either going to be directed over the device, as in a weir, or through the device, as in a flume. I mentioned in a previous slide that we need to know the depth of water flowing into that hydraulic structure, whether it's a weir or a flume. And so there are various different ways in which we can determine the depth of water. The first one is the float. You can see the float here, and as the water level increases or decreases, it's going to be able to send a signal and will record the depth. We can use electrical circuits so that as the water level changes, we can determine the level of the water by an electric current. We can use ultrasonics where we send sound wave down, and the time it takes that sound to bounce back will give you an indication of the distance between this and the water. And since you know the level of the bottom of the channel, you can determine the depth of the water at that time. We can have submerged pressure transducers. And again, if that's at the very bottom of the channel, then the depth of the water will change the pressure, and you can determine the depth of water from that change in pressure. There is another one called a bubbler, and I have I'll walk through this slide and then I'll show you a picture. But you have a tube that's in the stream. You push air through that so that bubbles are traveling through up the tube at a constant rate. As the depth of water changes, you are going to have to change the pressure to maintain that rate of bubbling. And from those changes in pressure, you can determine the level of water in that container. And here is what it looks like. Here's your air coming in. You get a certain rate of bubbling. As the water level drops, you're going to need less pressure to get the same rate. As the water level increases, you're going to need more pressure to keep that same rate. So again, by doing a little bit of math or letting the computer do that math for you, you can have an idea of the depth of the water at that point. Next few slides, we're really going to talk about weirs. Weirs are sometimes the simplest and least expensive ways of measuring flow. We're not going to use these for influent flow because influent flows have more solids in them than effluent flows. And you'll see in a couple of slides later on why you don't want solids accumulating upstream of the weir. Again, the depth of the water as it leaves the weir, as it goes over the weir, influences the accuracy of the measurement. So if those changes are going to be significant, maybe a flume will be your better choice. And again, when the water's over your head, it doesn't matter how deep it is. So again, if depth of water leaving the weir is of an issue, you might want to choose another method of measurement. So this looks at a few types of weirs. You can see here is a V-notch. Here are just straight plates. Here you see variations of the straight plates. V-notch weirs are probably better for small flows that are not going to change that much. Again, I put down here a website that if you want to pause this and write that down, or even just do a search under sharp crested weirs, you might find this website, depending on which browser you're going to use. This is a picture of a sharp crested weir. And here is some of the information and distances that you are going to need to have if you use the weir to make sure that it's working correctly. I'll come back to this slide, but essentially in your small regular flows that were mentioned earlier, you are going to have usually a maximum and of course a minimum height of that flow. We call this H. This is the maximum height or maximum head, and the depth of this weir has to be at least 2 to 3 times this depth. So if this depth changes, this weir has to be taller. Your level where you are going to take your depth, here is an ultrasonic sensor, has to be at least 4 times this maximum height. So you're not going to put this sensor down here. It's not going to work that well. This area under here, the water just can't trickle down. It has to flow over, and you need at least an air gap under this plate for this to be measuring the flow accurately. So this is the text. This is the words that go with the previous slide. So if you want to toggle back and forth as we're going through this. So the weir plate, the water is going to flow over, it has to be perpendicular to the flow. It has to be at right angles to the flow. It should be level, and the thickness of the weir plate should be less than 0.1 of an inch, and the distance from the weir crest to the bottom of the approach channel should not be less than 1 feet. In the previous slide, it says it was 2 to 3 times the height. So again, you're going to need a significant amount of flow for this to work well. The overflow sheet of water, we call this the nap, should touch only the upstream edges of the weir crest or the notch. It shouldn't be trickling down. It should be flowing freely over that plate, and therefore, because of that, you should see an airspace under that nap. And the measurement of the head, the depth of water, should be at a point 3 to 4 times the maximum depth upstream from the weir crest, or the maximum head, the pressure of that water. And to prevent you going back and forward, I've duplicated the slide here. Here is that distance. This should be greater than 1 foot, and it has to be at least 2 to 3 times the maximum distance between the flow and the weir plate. This sensor must be at least 4 times the distance from the weir plate based on this change in height. the water has to flow over this, and you have to have air that able to flow underneath this for this to work. Here is an example of a weir, water's flowing over this and getting a measurement. There's your, I think that's your depth, ultrasonic depth transducer there. The next few slides are going to talk about the other type of measurement using flumes. Of course, if you can't use a weir, then flumes might be your only other option. They can handle flows that have solids in them because their velocity as they flow through the flume is higher and it tends to clean itself. They are maybe a little more expensive to install. They usually come pre-cast, but they have to be leveled and make sure that they're not going to move. This is an example of a flume. You can see water flowing down here. Here's your transducer to measure the depth. Here's the constriction, and there's the outflow. This is called a partial flume, and it's very common. I think a lot of water treatment systems are very partial to it, but that doesn't mean that that's where it gets its name from. Sorry, I had to say this dad joke, guys. Just forgive me. So, what are the advantages of partial flumes? I mentioned earlier that because of the high velocity, they tend to be self-cleaning. They have the advantage being accurate over a wider range of flows than weirs because they are not flowing over something. They operate with a lower loss of pressure or head. Again, mentioned earlier that most of them are pre-cast, pre-formed, and so they don't have to be constructed on site. But you need to make sure that there is little turbulence during the flow of that water through the flume as possible. So some of the conditions that are important for partial flumes to work well. So you're going to have a uniform channel before the flume equal or greater than 15 times the channel width. So if the channel width at throat is a foot, then that channel needs to be at least 15 feet long. Again, the throat has to be level, the flume has to be level. It can't be tilted up or down for it to work well. You need to make sure that the walls are vertical so that you are not changing the depth of the water. Again, the measurement of the depth, the head measuring point using your little ultrasonic transducer or even a ruler, put that 2/3 the length of the converging sidewall. Make sure everything is level and make sure there's nothing in the water or the channel that can interfere with the free flow of the water. Here is that throat here. Here is your constriction, and your measuring point has to be at least 2/3 of this distance. This has to be level, and you can see the water coming through here, coming through this constriction, and then out the other side. Here is an example of a flume, and you can see the water. Here's your constriction into your throat. Here they have a ruler as a depth gauge. They're not using anything fancy. You just look at the depth and it will tell you what it is. So flow measuring devices in general are required for facilities greater than 50,000 gallons per day. This is a Kentucky regulation. Any flow measuring device must be accurate within 10%, plus or minus 10%. And although you're not going to need to calibrate something like a flume or a weir, any other measuring device, any other flow meter that you need is going to be needed to be calibrated. That can be on a scheduled basis, but whatever that basis is, please stick to it. You will also need calibration if you ever think that it may not be working correctly, if it's been repaired or replaced. And if you're using it as a measurement for chemicals, certainly before you add your chemical to the water, make sure it's calibrated, even if it's not on the regular schedule on a daily or weekly basis. And the reason why is because you want to make sure that you're adding the right amount of chemical, not too much or too little. If you add too much, you might get into problems, but you're probably wasting an expensive resource. And if you add too little, it's probably not going to be doing the job that you intend it to do. Some other considerations for flow meters: read them at the same time every day. And again, if you are any changes that may affect the treatment of the wastewater, sort of also check them. So a little bit of math as we go towards the end of this chapter. This is a simple conversion. We did this in a previous chapter. It's on your conversion is on your formula sheet, but we want to convert 435,000 gallons per day into million gallons per day. And the easiest way to do that is on your calculator to divide 435,000 by a million, and that should give us 0.435 million gallons per day. The other way you can do this is by moving the decimal point 6 places to the left. If we start here, we go 1, 2, 3, 4, 5, 6 to give us our 0.435. As a guide to solving problems in the manual and the study guide, and certainly on the test, make sure that the number of places of decimals for flow is at least 3. So don't round this to 0.44, use the 3 places of decimals. That way you will get as close to the answer that we will provide you on the math study guide or in the manual or on the test as possible. So here's another simple conversion where we're asking you to convert gallons per minute into gallons per day. We have 41 gallons per minute. So what is that in gallons per day? There are 60 minutes in an hour, 24 hours in a day, and that's 1,440 minutes in a day. So we take our 41, multiply it by 1,440, and that should give us something like 59,040 gallons per day. I'm not sure if this is on the formula sheet or not, but if it isn't, just remember 60 minutes per hour, 24 hours in a day, or you can just remember this number. this ends Chapter 8, Flow Measurements. And as ever, we've given you 2 ways to contact us with either comments or questions, either by email at envhelp@ky.gov or the phone number 502-782-6189. And as ever, we want to just remind you and encourage you to contact us with any comments or questions that you have. It's very important to you that we are able to help you as much as we can. Thank you very much. This concludes the presentation.